Mathematics in uncertainty. With this section of the IB chemistry, the essential idea that we have to take away is that all measurement has a limit of the precision and accuracy, and this must be taken into account when evaluating the experimental results. And main understanding that you have to gain from this section is that how to do the propagation of the random errors in data processing. Then we are going to figure it out how to report measurements in chemistry. In chemistry, every measurement must be reported carefully and consistently. And there are three parts to a measurement: so numerical value, the unit, and uncertainty. So for example, if we have the numerical value 2.63, then it should have a unit. So let's say it has a unit of centimeter cube and uncertainty of the 0.05 centimeter cube. And also don't forget that your measurement, right, your number, and the uncertainty should have same number decimal places. Okay, then let's discuss the rules of the significant figures, or SIFIC in short. So when we count digits such as the 1, 2, 3, 4, 5, 6, 7, 8, 9, these are considered as the non-zero digits, and these always count as a significant figures. So example, if we have something like 1245, this has 1, 2, 3, 4 for suffix. Okay, now let's discuss the zeros. When we have zeros, zeros are more complex. There are three situations in which they can occur. The first one is leading zero, second one is called captive zero, and the last one is called trailing zeros. So when you have a leading zeros, they are never significant. So what I mean by leading zeros is when you have something like 0.000182, these zeros in the front of your non-zero digits are called leading zeros. And these numbers are, of course, our non-zero digits, right? So in this case, we only have three suffixes. However, when you have captive zeros, or I sometimes call this a captured zeros, so when you have captured zeros, they are always significant because they are between non-zero digits. So for example, if we have something like 1.0082, these zeros are called captive zeros. And in this case, we have 1, 2, 3, 4, 5, 5 suffix. Okay, then let's look at the trailing zero case. So trailing zeros are a little bit different. Okay, so when you have trailing zeros such as 1200, since there's nothing to capture these zeros, right? So these are called the trailing zeros, and we don't count them as a suffix. So in this case, we have only two suffixes left. However, if when you have something like 1200 point, okay, in this case, because this point, the decimal point here, closes the zeros, right? The non-zero digits to capture these zeros here, this count as a suffix. So in this case, we have four suffixes. Same thing when you have something like 1200.00. In this case, this decimal point here helps these non-zero digits to capture these zeros and these zeros. So we count them as the suffix. So in this case, we have 1, 2, 3, 4, 5, 6, 6 suffix. So when you have scientific numbers such as 1.200 times 10 to 3, we don't care what's coming after this multiple sign. We just want the main numbers, right? How the main numbers look like. So in this case, we have a captured zeros, like captive zeros. So we have 1, 2, 3, 4, 4 suffix. Okay, then let's discuss the rules of the suffix in calculation. So when you have just like general multiplication divisions, the answers must have the same number of suffix as the pair with the fewest suffix. So means So when you have examples such as 3.46 times 2.1, we have number 7.266, right? However, so we count how many suffixes are here. We have 3 suffixes here, and we have 2 in this side, right? So su suffix. So we have to leave our answer with the 2 suffix. So we're going to say we are going to round this up here. So the final answer is 7.3. This is the correct number. And when you have addition and subtraction, the answer must have the same number of the decimal places, okay, as the original number with the fewest decimal places. Okay, then when you add something like 12.11 with 18.0, the answer is 30.11. However, this is not the final answer, right? This is not the final answer yet because we need to have correct number specific. So you can see that the first number has 2 decimal places, right? Second number has only 1 decimal places. So since we are going with the fewest decimal places, our final answer should be 30.1. And this is the final answer for this case. Then let's talk about how to propagate uncertainty in calculation. So when we have the addition and subtraction in calculations, okay, we have to add the absolute uncertainties together. So here in the example, the change in temperature of the mixture can be found by the subtracting the initial form from the final temperature. So if the liquid started at 18.0 degrees Celsius plus minus 0.5 degrees Celsius and ended up at 25.0 Celsius plus minus 0.5 degrees Celsius, then the change in temperature is. So in this case, we are doing the delta t equals t final minus t initial, or we are trying to calculate the difference between the final temperature and initial temperature. So what we need to do is we're going to subtract the initial temperature from the final. So we do 25.0 degrees Celsius plus minus 0.5 degrees Celsius minus 18.0 degrees Celsius plus minus 0.5 degrees Celsius, right? Then when you do this, this is same as 25.0 minus 18.0 plus minus 0.5 plus 0.5 because we are adding the absolute uncertainties together. And final answer is 7.0 plus minus 1.0 degrees Celsius. Okay, you don't have to write the unit just like every single time you write your measurement and or uncertainty. You can just write once at the end. Okay. Okay, let's do task number 9. So here we have 10.0 centimeter cube of exit, which is delivered from a 10 centimeter cube pipette that has uncertainty 0.1 centimeter cube and repeated 3 times. What is the total volume delivered, right? So in order to calculate the total volume, since we know that this is delivered 3 times, we can just simply do 10.0 times 3, right? For the measurement part. So this is same as 30.0 centimeter cube. And then for the uncertainty, since we're just adding it 3 times, we can also say it is same as 0.1 times 3. So this is same as plus minus 0.3 centimeter cube. So the total volume for this case is same as 30.0 plus minus 0.3 centimeter cube. Okay, then let's do task number 10. So when we are using a burette with the uncertainty 0.02 centimeter cube, you subtract the initial volume from the final volume. And the final volume is equal to 38.46 plus minus 0.02 centimeter cube, and initial volume is same as 12.15 plus minus 0.02 centimeter cube. What is the total volume delivered? So in this case, since we have to calculate the total volume delivered, we can just do volume total is same as volume final minus volume initial, so we can do 38.46 plus minus 0.02 centimeter cube minus 12.15 plus minus 0.02 centimeter cube, and this is same as 38.46 minus 12.15 plus minus, we are adding the uncertainties together, so this is same as 0.02 plus 0.02 centimeter cube. Then final answer is same as 26.31 plus minus 0.04 centimeter cube. Okay, now let's talk about how to propagate your uncertainty during the multiplications and divisions. So when we are doing multiplication and divisions, the way we propagate our uncertainty is different from when we add and subtract the numbers. Okay, so in this case, we have to calculate something called percentage uncertainties, and then we have to add them together for the final value. Okay, so in order to calculate the percentage uncertainty, what we need to do is we have to use a formula called the percentage uncertainty. The percentage uncertainty is same as absolute uncertainty divided by the measurement and times 100. So absolute uncertainty is like your measurement uncertainty, right? Also, what you need to remember is when you do calculation, you add this percentage uncertainty for the final value, right? However, when you are writing your final answer, with your absolute uncertainty values. So what I mean by this is that you have to convert your final percentage uncertainty value back to the absolute value. So let's do an example together. So example, an object has a mass of 9.01 gram plus minus 0.01 gram as uncertainty. And when it is placed in a graduate cylinder, it causes the level of the water in the cylinder to rise from 23.0 centimeter cube to 28.0 centimeter cube. And this cylinder has the uncertainty of 0.5 centimeter cube. And we need to calculate the density of the object. So density, calculate the density, what we need to do is we have to divide the mass by the volume, right? So we first have to calculate our volume. So let's do volume. The final volume is same as volume final minus volume initial. The final volume is 28.0 plus minus 0.5 centimeter cube. Initial volume is same as 23.0 plus minus 0.5 centimeter cube. Then we can say that the final volume is 5.0 plus minus 1.0 centimeter cube. Okay, and that the mass of this object is same as 9.01 gram plus minus 0.01 gram, right? But since we have to divide this number, the mass by the volume, we have to convert our absolute uncertainty to percentage uncertainty. So the percentage uncertainty of this mass is same as 0.01 divided by 9.01 times 100, which is same as about 0.11%, right? And then same thing with the volume, since uh, percentage uncertainty of volume is same as 1.0 divided by 5.0 times 100, and this is same as approximately 20%, right? Then we can say that the density in this case is same as 9.01 gram plus minus 0.11% divided by 5.0 centimeter cube plus minus 20%. Okay, then this is same as 9.01 gram divided by 5.0 centimeter cube plus minus 0.11% plus 20%. Then the final answer, or the just like the calculated answer, is 1.8 plus minus 20.11%, right? But since we need to convert our percentage uncertainty back to absolute uncertainty, what you're going to do is we're going to use the formula, but we're going to go backward. So we know that 20.11% is same as the absolute uncertainty over 1.8, right? Then we know that this our absolute uncertainty is same as 0.4. So the final answer is 1.8 plus minus 0.4 gram per centimeter cube. Okay, then let's talk about the rules for multiplying or dividing by a pure number. So a pure number is a number without an estimated uncertainty. And then in order to propagate the uncertainty for this case, we have to multiply and divide the absolute uncertainty directly. So let's do example together to figure out what that means. Okay, so here we have to convert the 3.62 gram of the magnesium into moles, right? So we have measured the magnesium, right? The mass is 3.62 gram with uncertainty 0.01 gram. Okay, so molar mass of the magnesium is approximately 24.3 gram per mole. Okay, so we know that to calculate the mole, we have to convert the 3.62 gram to 1 mole, right? So 24.3 gram, and then it's about 0.149 gram more. Okay, then now to calculate uncertainty, we're just calculating the percentage uncertainty. So we do 0.01 gram, right? The absolute uncertainty divided by the measurement 3.62 times 100. So in this case, the percentage is 0.28%. Okay, but when we are writing our final answer, make sure you convert your percentage uncertainty back to the absolute uncertainty. So in this case, we have 0.0004 more. So final answer is 0.149 plus minus 0.0004 more.